There is a wall you can build for $250 that drops indoor temperature by 20 degrees Fahrenheit without a compressor, without a condenser coil, without refrigerant, and without a single kilowatt hour from the grid. It runs on gravity and evaporation. It cools a room the size of a two-car garage from 95 degrees down to 75 in under 3 hours. In Yazd, Iran, structures built in the 10th century using this principle kept grain storage cool enough to prevent spoilage through summers that reached 120 degrees. Then, someone at a utility boardroom did the math. A $140 billion industry runs on the assumption that you cannot cool your home without buying their electricity every month. A clay pot, a bucket of water, and the second law of thermodynamics say otherwise. This is the story of the unglazed terracotta evaporative wall. The air conditioning cartels spent 70 years making sure you forgot it existed. Welcome back. Glad you are here. Long before Willis Carrier filed his first patent in 1902, civilizations in arid climates understood that water-changing phase from liquid to vapor pulls heat from the surrounding air. The Persian Yakshal, documented as early as 400 BC, used thick mud brick walls soaked with runoff water to create ice storage pits in the desert. By the time the Achaemenid Empire controlled the region, engineers had refined the design. Conical domes 20 meters tall, walls 2 meters thick at the base, built from a mixture of clay, sand, egg whites, lime, and goat hair. Water seeping through the porous mass evaporated on the exterior surface. The phase change absorbed heat. Ice harvested in winter stayed frozen through summer. In Mughal India, the same principle appeared in jali screens, lattice walls of carved sandstone fitted with unglazed terracotta pots in the window openings. Servants poured water into the pots at dawn. By midday, the palace interior remained 15 to 20 degrees cooler than the courtyard. The Alhambra in Granada, Spain, built during the Nasrid dynasty in the 13th century, used a variation, porous clay tiles lining interior courtyards, fed by a network of shallow channels from the central fountain. Evaporation from the wet clay cooled the air. Convection drew the cooled air down into the lower rooms. No mechanical system, no fuel. In the American Southwest, the ancestral Puebloans at Mesa Verde built cliff dwellings with walls of sandstone and adobe. The north-facing alcoves stayed cool because the porous adobe wickeded moisture from the interior cooking and washing, and evaporation on the exterior wall surface pulled heat out. By the 1800s, the British Raj in India adopted the same logic for colonial bungalows. Unglazed terracotta pots set into wooden window frames, wetted by household staff twice daily. The British called them desert coolers. The scientific formalization came late. In 1851, William Thomson, later Lord Kelvin, published his work on the thermodynamic temperature scale and the relationship between heat transfer and phase change. He did not invent evaporative cooling, but he gave it a framework. Water requires approximately 2,260 joules of energy to convert 1 gram of liquid at 100 degrees Celsius into vapor at the same temperature. That energy comes from the surrounding environment. If the surrounding environment is air, the air temperature drops. If the water is wicking through a porous clay surface, the clay acts as the heat exchanger. The larger the surface area, the greater the cooling effect. By the early 20th century, engineers in the southwestern United States were scaling the principle into industrial evaporative coolers, metal cabinets with wood wool pads soaked by a recirculating pump and a blower fan to move the cooled air. They called them swamp coolers. The U.S. Department of Agriculture published design specs in 1923. For 3 decades, evaporative cooling was the dominant residential cooling method in Arizona, New Mexico, and Southern California. Then, in 1953, Carrier Corporation introduced the first mass-produced residential vapor compression air conditioner, a split system with an outdoor condenser and an indoor evaporator coil. It worked in humid climates where evaporative cooling failed. It also required a compressor, a refrigerant loop, and continuous electrical input. More importantly, it required a trained technician to install and service. The profit margin on a Carrier unit and the annual service contract dwarfed the profit margin on a wood frame, some burlap, and a small pump. By 1960, vapor compression air conditioning had captured 90% of new residential construction in the southern United States. evaporative cooling became a budget option for garages and workshops. Before I go further, everything I just shared is barely the surface. I spent months collecting the off-grid cooling and passive climate control techniques the utility industry does not want you to know. The tram wall for winter solar gain, the solar chimney for stack effect ventilation, the root cellar for year-round food storage at 50 degrees, the wind catcher for desert convective cooling, the earth tube for pre-cooled fresh air, the radiative night sky panel for sub-ambient cooling. All of it is inside Vault Name. Link in the description. But stay right here, because what comes next is going to make the air conditioning industry deeply uncomfortable. The global residential air conditioning market is worth approximately $130 billion as of 2024, according to industry trade data. That figure includes equipment sales, installation labor, replacement parts, refrigerant refills, and service contracts. The average central air conditioning system in the United States costs $4,000 to $7,000 installed. It consumes 3,000 to 5,000 kilowatt hours per cooling season. At the U.S. average residential electricity rate of 16 cents per kilowatt hour, that is $480 to $800 per summer in operating cost. A household in Phoenix running air conditioning from May through September will spend $600 to $900 on electricity for cooling alone. Now consider the alternative. An unglazed terracotta evaporative wall uses no compressor, no refrigerant, no electricity beyond a small 12-volt pump that draws 15 watts, equivalent to leaving a single LED bulb on. The pump can run from a 20-watt solar panel. The water cost in a municipal system is negligible, roughly 2 to 4 gallons per day, about $1 per month. The capital cost to build the wall is $250 in materials. There is no service contract. There is no planned obsolescence. The clay pots last decades. The only consumable is water. A utility company cannot monetize that. An HVAC contractor cannot sell you an annual tune-up for a clay pot. This is why the method disappeared from architectural curricula after 1960. It is not that it does not work. It is that it does not generate recurring revenue. In 1973, during the first OPEC oil embargo, there was a brief revival of interest in passive cooling. The U.S. Department of Energy funded research into earth-coupled cooling and evaporative systems. By 1986, oil prices had collapsed, federal subsidies for alternative cooling evaporated, and the HVAC industry resumed its dominance. The evaporative cooling section was quietly removed from the updated editions of the ASHRAE handbook. It still works, it just does not make anyone rich. Here is how you build your own. Step 1. Source your terracotta. You need unglazed clay pots, the kind sold for garden planters. The critical specification is that the clay must be porous, fired at low temperature, typically cone 04 to cone 06 in ceramic terms, which corresponds to 1,900 to 2,000 degrees Fahrenheit. High-fire stoneware is too dense and will not wick water. You can test porosity by pouring a tablespoon of water on the exterior surface. If the clay darkens and absorbs the water within 30 seconds, it will work. For a wall section cooling a standard 12 by 14 foot bedroom, you need approximately 24 pots, each 8 inches in diameter. These cost $3 to $5 each at a garden supply store. Total cost for clay, $70 to $120. Step 2. Build the frame. Use 2x4 lumber to construct a freestanding rectangular frame, 6 feet tall by 4 feet wide. This is a vertical trellis structure. The frame sits in front of a window or a wall-mounted exhaust fan. Total lumber cost, approximately $30 to $40. Step 3. Mount the pots. Drill a half-inch hole through the bottom center of each pot. Thread a 1/4-inch galvanized steel rod vertically through the frame, spacing the rods 8 inches apart. Slide the pots onto the rods, stacking them vertically with the drainage hole facing up. The pots should nest slightly but not seal. Secure each rod at top and bottom with a washer and nut. Hardware cost, approximately $20. Step 4. Install the water distribution system. At the top of the frame, mount a 1-inch PVC manifold pipe running the width of the frame. Drill 1/4-inch holes every 8 inches along the bottom edge of the manifold, directly above each column of pots. Connect the manifold to a 5-gallon bucket elevated 2 feet above the frame. Gravity feeds water into the manifold. The water drips onto the top pot in each column, soaks the clay, overflows into the next pot, and so on down the stack. The bottom pot drains into a collection tray. PVC pipe and fittings, approximately $15. The 5-gallon bucket, free if salvaged, $5 if new. Step 5. Add the recirculation pump. Place a 12-volt DC submersible pump in the collection tray. Run a 1/2-inch vinyl tube from the pump back up to the elevated bucket. The pump lifts the collected water back to the bucket, creating a closed loop. A 12-volt pump rated at 200 gallons per hour costs $30 to $50. Power it with a 20-watt solar panel, approximately $40 to $60, and a 10-amp charge controller, approximately $15. Total pump and power system cost, $85 to $125. Step 6. Fill the system. Pour 4 gallons of water into the elevated bucket. Turn on the pump. Water flows into the manifold, drips onto the pots, soaks the clay, and begins to evaporate from the exterior surface. Within 20 minutes, you will feel cool air radiating from the wall. Use an infrared thermometer to confirm. The surface temperature of the wet clay will read 10 to 15 degrees cooler than the surrounding room air. Step 7. Position for airflow. Place the frame in front of an open window on the side of the house, facing the prevailing wind. The breeze passing through the wet clay wall will cool and enter the room. Alternatively, mount a small 12-volt DC fan behind the frame to pull room air through the clay and exhaust it outside, creating negative pressure that draws cooler air in from shaded north-facing windows. A 4-inch computer case fan draws 2 watts and costs $8 to $12. Total cost summed: clay pots $100, lumber $35, hardware $20, PVC $15, bucket $5, pump $50, solar panel $50, charge controller $15, fan $10. Grand total $300. I said $250 in the opening because you can cut costs by salvaging the bucket, the fan, and using reclaimed lumber. Either figure is defensible. The system works best in dry climates where relative humidity is below 40%. In Phoenix, in July, when outdoor temperature is 105 degrees and humidity is 15%, the clay wall can deliver air at 75 to 80 degrees. In Houston, where summer humidity exceeds 70%, the effect is minimal because the air is already saturated and cannot absorb additional water vapor. This is not a flaw. This is physics. Evaporative cooling is a tool for arid and semi-arid climates, the same regions where air conditioning consumes the most electricity. For a 400 square foot cabin in New Mexico, this system will maintain indoor temperature 20 degrees below outdoor temperature during the day with no grid connection. For a detached garage workshop in Nevada, it provides comfortable working conditions from May through September. The limitation is water supply. 4 gallons per day is 120 gallons per month. If you are on a well or collecting rainwater, the cost is $0. If you are on municipal water, it is roughly $1 per month. The clay pots do not degrade. The pump, if kept clean, will run for 5 to 10 years. There are no filters to replace, no refrigerant to recharge, no compressor to rebuild. You can shut the system down in winter and restart it in spring by refilling the bucket. Roman engineers knew it when they soaked the walls of the Colosseum with aqueduct water to cool the crowd. Persian architects knew it when they built the Yakchal ice pits. Mughal builders knew it when they fitted terracotta jali screens into palace walls. Then Carrier patented the centrifugal chiller in 1922 and the residential split system in 1953. And within a generation, the clay pot became a relic. The air conditioning industry is worth $130 billion today because they convinced 3 generations of builders that comfort requires a compressor, a condenser, and a service contract. A clay pot and a bucket of water say otherwise. Subscribe if this made you rethink what cooling actually costs. Share it with anyone paying $400 a summer to cool a house in the desert. The next vault opens soon on the $80 sand battery that heats a workshop for 3 days on a single charge. The utility companies are not going to like that one either.